All right, so today we're going to turn our focus from all these angle relationships and start looking at segment lengths, tangents, secants, chords. As they intersect, obviously they create angles, but there are also segments that we want to be able to find lengths of. They'll tell us distances between points that could be useful to find later on. And then we'll talk about putting a circle into the coordinate plane and how to write the equation of that circle, writing the equation of that function, which will help you as you progress into pre-calculus or trig stats next year. So some new ideas we want to get to. First are the segments in the circle. So the idea is, yes, tangent is a line, secant is a line, chords are segments, but as these guys start to intersect with each other, we can, I mentioned before, cut these lines down to talk about segment pieces and find some distances. So when two chords intersect, here's a definition for you. When two chords intersect in the interior of a circle, of course, is where they're going to intersect. Then each chord is divided into two segments that are called segments of a chord. Just makes sense, right? Now, all of these theorems that tell us how to find these segment lengths or what the relationships are in these segment lengths are fine, and we'll talk about what the theorems say, but really what we got to focus on is where are these segments intersecting, right? So here's the first example here where we've got two chords that are intersecting, and if two chords are going to intersect, they're going to intersect on the inside, right? So they're intersecting inside. And when this happens, this theorem basically says that the segments of the chords, if you multiply them together, will be equal to each other, right? So in this particular example, AM and MB are segments of one chord. If you multiply AM times MB, then that'll be equal to multiplying the other segment chords together. So ZM times MY. And to write that out would look like this. Okay? And you can color coordinate these. But, so again, these are intersecting inside the circle. Right? And when that happens, yeah, this is fine. AM times MB equals ZM times MY. Another way to look at this is piece times piece equals piece times piece, right? Kind of like what we did with our right triangles. But if you multiply the pieces of each chord together, they should be equal to each other. Okay? So, for an example here, we've got two chords that intersect, the intersections inside the circle. So we need to go piece times piece equals piece times piece. Sort of an oversimplification of that theorem. So we'd go 4 times x has to equal 6 times 8. So you get 4x equals 48. Divide both sides by 4. And x is 12. Right? And so there you go. All right? So that's what happens when you have two chords that intersect. Now we're going to take a look at segments and secants and when they intersect. Okay? And what happens then. So secant segments, segment that contains a chord of a circle and has exactly one endpoint outside the circle. Right? So anytime we talk about a secant intersecting with something, then we're talking about intersecting outside the circle. The part of the secant segment that is outside the circle is called the external segment. Just makes sense. So some vocabulary there for you to remember. Make sure you remember that. Right? And that helps us get into the theorems and what the words are trying to say. Right? So if two secant segments... back up. If two secant segments share the same endpoint outside the circle, then the product of the length of one secant segment and the length of its external segment equals the product of the length of the other segment. It's a lot of words, right? So basically what this is saying is, all right, these guys are intersecting outside the circle. right? So the theorem is all well and good if you want to use proper geometric terms, and we really should know those terms and use them. But the bottom line is this. If your two segments intersect outside the circle, then what ends up happening is if you take the outside piece times the whole thing for each secant segment, then those products will be equal to each other, right? So here, PQ times PR would be equal to PS times PT. So in other words, if you take the outside times the whole thing, that is going to be equal to taking the outside times the whole thing. And this is going to be a common theme for any time two segments intersect outside the circle. So outside times whole equals outside times whole. That's the deal. Okay? So, for example, if we got two secant segments that look like this, then we want to take the outside times the whole thing and set it equal to the outside times the whole thing. And if we do that here, the outside piece of this secant is 7. The whole thing is going to be 7 plus 6, or 13, right? And same thing for the other side. The outside piece is 4. The whole thing is going to be 4 plus x. And so that's the equation that you must go solve. So you get 91 here, 16 plus 4x. Subtract 16 from both sides, and you will get 75. Let me check my math really quick, and that does sound about right. And so now you divide both sides by 4. And since we're talking about lengths, it does make sense to go ahead and get a decimal answer here. So x is going to be 18.8. Okay? And just remember that we do not go by the picture here, right? So anyway, that's what happens when your segments intersect outside. Okay? All right, well, here we've got a secant segment and a tangent segment that are intersecting. But look, they're still intersecting outside. And when that happens, we're still going to take the outside piece times the whole thing, right? So these guys are still intersecting. So these guys are intersecting, like I said, outside the circle. Right? And so we're going to take the outside piece times the whole. We're still going to do that. Outside piece times the whole equals outside piece times the whole. Now, watch what happens. Right? For the secant segment, there's no problem. Outside piece is PQ. The whole thing is PR. Right? Which is where the PQ and the PR come from. Now, over for the tangent segment, the outside piece is PS. But then the whole thing is still PS. So, in other words, you just end up squaring PS. So, but I like to stay consistent with the outside piece times the whole thing. That just kind of ends up making more sense to me. Because it's intersecting outside, we're going to use the same rule. Okay? So, for example, we're looking at a problem like this. So, intersecting outside, then we want to do outside piece, which is x, times the whole thing, which, hey, look at that, looks to be x'd again. Outside piece here is 6, times the whole thing, which is going to be 10, right? So this is going to be x squared equals 60, square root both sides, and again, we're talking about a segment length, so, I mean, you could reduce it down to 2 square root of 15, but going ahead and calculating out the square root of 60 makes enough sense as well. So we get 7.7. Okay? Sticking with the outside piece times the whole thing. That's it, right? Those are the only types of examples. If we go back, right, and stick with this outside piece times the whole thing, right, before we get to these mixed examples here. Right? What if we have a circle and two tangents, right? Well, and we'll call this what? A, B, and C here, right? We can keep using the outside piece times the whole. Since these are tangent segments, now we should already know from the snow cone theorem that AB is going to be equal to AC, right? But if you wanted to lump this into the outside piece times the whole thing, you could. Outside piece here would be AB. The whole thing is AB, which is just going to be AB squared. Outside piece is AC times AC, which is just going to be AC squared. But look at that. If you square root both sides, you get back to AB equals AC. So even out here, you can do outside piece times the whole thing equals outside piece times the whole thing, right? It still works. Okay? Now, exit tickets. So somewhere, scratch out the work for these mixed example problems. This is called an exit ticket quiz, but obviously we're not using it for that. So take a second, set up this equation, and solve it. You can stop the video, and then when you're done, start it back up and check and see if you're right. And we'll do this for all the next couple of 2 or 3 problems, right? But find some place in the margin to scratch this out. Okay, so what'd you do? These guys cross inside. So I want to go piece times piece equals piece times piece. So go 6 times 10 equals 5 times x. We go 60 equals 5x. You don't want to do outside piece times whole here because there is no outside piece, right? The only thing you have to remember is that you don't want to use the whole chord here in your equation. It is the pieces, which would be a little bit confusing, but you got to find some way to remember that. All right, but that's that one. And here's the next problem. Take a second, try it, start the video back up. Okay, so these guys cross outside. So we need outside times the whole equals outside times the whole, right? So outside piece for the first segment is 3 times the whole thing is 3 plus x equals 4 times the whole thing is going to be 11, right? Make sure that you add the 4 and the 7. And then solve. And so 3x is equaling 35. And so x is ended up being 11.67, right? Okay. Next. Try that. Stop the video. And again, these guys are crossing outside. So go outside piece times the whole thing. Look at that. X and x, the outside piece and the whole thing are exactly the same. And then we go outside piece times the whole thing. And so we go x squared equals 81. Square root. And it would be plus or minus 9, but we can't use the negative 9 segment length, so x just ends up being 9. Okay? So hopefully that makes enough sense and gets you into your homework and give those a shot. Again, the question, and we did this for the angles, so we can do this for the segments too, right? Somewhere in the margin, basically, you're going to ask yourself, where do the segments cross? Right? And if they cross outside, then we want to do outside times the whole equals outside times the whole. And if they cross inside, then we're just going to do piece times piece equals, and maybe we should write it out to make it make more sense. I don't know, whatever makes more sense to you. Right? So now we do have some formulas to use for our angles. You just got to make sure that you understand if you're trying to find angle measures or arc measures, or if you're trying to find segment lengths. And then we dive into these shortcuts, these questions that we have to ask ourselves. Okay? All right. The last thing here, writing and graphing equations of a circle. This is incredibly easy, right? Once we understand where this comes from. Right? Let's say that we've put a circle into the coordinate plane. and we want to, say, find the radius, right? The radius of the circle is going to be the same. Well, we got to find some point, and we put this circle in the coordinate plane so that the center is at 0. Okay, that's the idea. Well, we want to find some point on the circle, right? Some point on the circle right here. That is a point, and we need coordinates. I'm not going to use x and y, and the reason why I'm not going to use x and y is because actually I'm going to use x and y, and we should. Anytime we write the equation for a function, we always have an x and a y in that function so that it will represent a point on the graph. So the points on the graph we should let be x and y. Now, our radius is here at 0, 0. Or, I'm sorry, our center is here at 0, 0. Right? If I want to find the length of this radius, then I could treat this like walking downtown Indy, right? If I wanted to go from the origin to that point on the line, then I would want to walk over so far and then walk up so far, right? That's not the most direct way to get that distance, but that's what we'd want to do. So if we do that, then what we've created here is a right triangle, right? And so we could use Pythagorean theorem. All right? So the distance from the origin to the point on the circle means that we're going to walk so far in the x direction, so we'll just call that x, right? And then we're going to walk so far in the y direction, so we can call that length y. Okay? So it makes sense. To get to x comma y from the origin, you have to walk over x and up y. And those are going to be those distances that they're going to walk. Well, we're in a right triangle, and if this distance is x, this distance is y, and we're letting this be the radius of the circle, which it is, then Pythagorean theorem would look like this. Right? R squared equals x squared plus y squared. And that's because the center is at the origin. If we move the center anywhere off of the origin, then we can't use 0, 0 anymore, right? And so we want a generic form of this equation. So we have to sort of consider what happens if we move the circle off from the origin. And now your center is here. Right? Well, this point is still going to be x comma y. And now we have to give some variables for the center because we don't know where that center is. It's customary to use h comma k. That's kind of what we used for the vertex in quadratics from Algebra 2, right? So we'll keep using that for circles. H comma k just ends up sort of being the default variables to use, okay? Well, now if we want to go from the center to a point on the circle, and those lines aren't exactly straight, but you get the point, right? Now we have to find a way to represent this distance. So we're still going to walk over x and up y, but it's not going to be quite as easy as x and y because we have h here and then over x here. So this is kind of weird. But to find that distance, we'd have to take x minus h. Find the difference in those coordinates. And do the same thing here. We'd have to find the difference in those y coordinates. Right? It's basically the distance formula. Right? So what this all means is that when it's all said and done, we get an equation that looks like this. If the center of the circle is not at the origin, then we have the center at h comma k. And to go from the center to a point on the circle, we'd have to go so far in the x direction. This is how to find that distance. Subtract the x's between the center and the point on the circle, and then subtract the y's. And then we're going to square those, and that's going to be equal to the radius squared. And that all comes from Pythagorean theorem from a right triangle. Okay? But that's it, right? X and Y, we're not going to worry about plugging anything in for because we need the X and Y to represent any point on the circle. So it just turns into that. So we're going to end up finding the center and plugging the center in for H and K, and then finding the radius and plugging the radius in for R there. Okay? That's what we're going to use to write the equation of a circle. That's what we're going to use to graph. All right? So, for example, here's the function that's in whatever you want to call it, right? Center form or standard form or whatever. But we want to graph the circle. Okay? Well, we know that we need the center and we need the radius to graph this. The center just comes from these points. Okay? Now, if we go back for a second, recognize that we're supposed to be subtracting these x coordinates and subtracting these y coordinates. So when we see a plus inside of here, in these parentheses, that means that we must have had an x minus a negative 3. So that means that the x coordinate for the center had to be at negative 3, and then the y coordinate had to be at 5. So we're going to switch the signs when we pull the center out. Negative 3 comma 5 puts us right, negative 3 comma 5 puts us right here. And then the radius, that's supposed to be the radius squared. So we've got a square root 16, and the radius ends up being 4. So now we would just use the grid lines and the fact that the radius is 4 and count 4 places over. 1, 2, 3, 4. We put a point on the circle there, a point on the circle there, 1 there, and then 1 here. And then you would want to draw a very nice, perfect circle, just like that one. All right, maybe it's not perfect, but hopefully you get the idea. All right? All right. So again, think about this for a second. Where's the center? Where's the radius? Okay? Are you considering the center here to be at 2 comma 5? That's where it's going to be. We're going to switch the sign and pull in the center out. And then what's the radius? Well, square root the 9, and the radius is going to be 3. Okay? So 2 comma 5 is right here. Since the radius is 3, we're going to go 3 in all directions to kind of give us an idea of different points on the circle, and then draw a nice, perfect circle. That's it. That's all there is to it. Okay? Now, if we want to write the equation of a circle, right? Well, we're still going to use the same idea, right? Where we go x minus h squared plus y minus k squared equals the radius squared. Okay? So the center is at negative 1, 3. So at negative 1, we go x minus a negative 1 plus y minus 3, and then we can go x plus 1 plus y minus 3, and we need the radius, right? We'll go into the graph. The radius would be represented by that segment right there, right? How do you find the distance from the center to a point on that graph? Well, distance formula, right? That's how we find the length of a segment. So we'd want to subtract the x's and subtract the y's, square them, and go through this whole rigmarole. So negative 4 squared plus negative 3 squared gets you 16 plus 9, which is 25, and the radius is going to be 5. So now we got to put 5 in here and square it, which by the time we're done simplifying this, it just turns into x plus 1 squared plus y minus 3 squared equals 25. Okay? So if we need the radius, just go find it. If we've got a point on the circle in the center, then we use distance formula to find that radius. Okay, a little bit of work, but hopefully not too tough. All right? Here, write the equation of the circle by finding the radius and the center. Where is that center? Well, that center would be here because it's 1, 2, 1, 2, 1, 2, the same number of grid lines in all directions. So that's your center, and those coordinates are at 0, 2, and then the radius is, well, we go 2 in every direction to get to a point on the circle, so the radius is going to be 2. This becomes really easy. X minus 0 squared plus y minus 2 squared equals 2 squared. Well, x minus 0 is just x. So the way you'll see this written is x squared plus y minus 2 squared equals 4. So if there's not anything in parentheses with x or y, then that tells you that the coordinate for the center is going to be at 0. Okay? And that's it. Even easier than that is if you know the center and the radius already, this becomes really, really easy. X minus 3 squared plus y minus 3 squared equals, make sure that you square that 4 and get 16. And that's your equation in standard form. Okay? So that tells you a little bit about graphing and writing equations of circles. All right, that's it. Get to your homework out in Canvas, and we'll see you next time.